here comes Cosmo, speed of light, ready to interact with neutrons, or is it with neutrons and photons, Cosmo, both of them. Did you enjoy the lecture? Interactions of gamma rays and electrons for electric cross-sections, thinking about interactions of neutrons with matter, collisions with hydrogen, absorption by chlorine, all of the elements of neutron logs. What do you think, Cosmo? What's the energy about neutrons? Should we go for them? What do you think, man? Do you like the lecture? Stay tuned and let's go for the next one very soon. Hello again, welcome back after your break. I hope you had a chance to recharge the batteries. The first part of the presentation took a little bit longer than I expected, an hour and 40 minutes, I think, 35 minutes. So I'm breaking this up into two video recorded lectures. The second part, which is the practical part, is about examples. We are going to conduct examples on the usage of the interpretation charts, density, PEF density, and neutron and density logs. And we're going to apply those to several cases that I have prepared, cases of clean clastic sequences, cases of carbonate sequences, cases of shaly sequences, cases of mixed sequences with light fluids, and so forth and so on. The objective is to recognize to understand how to use the cross plots. What are the mechanisms? What are the things that we have to pay attention to? How to assess dominant mineral composition? How to understand the effect of light fluids in the rock and what consequences the light fluids have on the cross plots, on the assessment of the cross plots. What are the mechanisms that I have to worry about? For instance, presence or not presence of bad caliper points, presence of thin beds, for instance, things of that nature. What happens when I have more than two mineral components in the rock matrix, things of that case. So I'm going to go in extreme detail at the beginning, and then we're going to summarize the cases, go one by one. And the last element of the presentation is the one in which I show the typical cross plot between photoelectric factor and spectral gamma ray logs to assess dominant clay minerals in the rock. Okay. The first thing that I want to mention, which is very important here, is the following. Regardless of how we do this, regardless of how we approach this technique, we always have to pay attention to all the well logs. Even though this lecture is about PEF, density, neutron logs, it's important that all the assessments that we do are in consistency with the remaining logs, gamma ray logs, resistivity logs, sonic logs, you name it, everything else. But also, it's very important to always do quality control and reality check, which is go and look at your rocks, EBUCAT, core data, core photographs. Let's look at the mud logs. Everything is very important. You know, I've been saying that well logs represent averages, volumetric averages of property. So certain things that might be important are swallowed, so to speak, by the volume of investigation. So it's very important that when we look at rocks, we understand their complexity and how that complexity has been averaged by the well logs and what consequence it has on our calculations of flow and storage properties of those rocks. Okay, take a look at that, reality check, pay attention to your rocks, look at the rocks, very important. With that said, let me first introduce the PEF density cross plot. This is the version of Schlumberger, so-called Lith 3 plot for the litho density tool. There are other cross plots that they have. For instance, for LWD, we have different cross plots. Different logging companies will have different plots. This plot in particular doesn't change a great deal, but let me explain what this is. First of all, before we ever use this plot, before we ever lay points from well logs on this plot, we have to understand whether and analyze whether those points are affected or are not affected by caliper, presence of barite in the mud, or bed thickness effects, or shell or clay. All of these things can affect the analysis. So I'm going to make the assumption that first of all, you verify all of those things. In due course, I'm going to point out possible problems. But here's the thing. On the x-axis, we have the photoelectric factor. The values that we have here are not larger than 6.2 barns per electron. Those are the units of these photoelectric factor. Now you know where it comes from, and the units are because it's convenient to have something that varies between 0 and 6. On the y-axis, we have the bulk density. And please note that the bulk density is reversed. So the highest densities are the bottom, 3.0, and the lower densities are at the top, 1.0. Now, we have 3 guides. And the guides, these are just for guidance. Actually, we have 5 guides, but 3 important ones. These guides are for the 3 main lithology, so to speak. One is for quartz or sandstone. There you go. Then we have the dolomite, and then we have the calcite. And the minor lithologies are the salt and anhydrite at the bottom, right here. So we have those. Please note that this particular cross-plot, the Lith 3, makes the assumption that the fluid that we have in the rock is fresh water. So everything will work fine if your rock has only one fluid, and the fluid is fresh water. There's a similar plot when the fluid is water, a little bit saltier, and things get changed a little bit. But I always like to use this one because this is the most common one, especially if your rock has been embedded with freshwater-based mud. And given the fact that the PEF and density measurements are relatively shallow sensing, most of the time they will be sensing the fluid in the mud rather than the fluid in the formation. There are exceptions, of course, but we have to take that into account. If you happen to have oil-based mud, then sometimes this can modify the situation slightly, so we also have to take that into account. Okay, now, having said that, let me just show you what the different guides are. If you go to the bottom of each one of those guides where it says 0, that will be the expected value of the properties for that rock if the rock had 0 porosity, solid component. You can actually see that if you go to the end of these guides, the corresponding density which you measure on the left axis here will be 2.87 for dolomite, 2.87 grams per cubic centimeters for dolomite. And if you go and do the same thing for sandstone, it will be 2.65 grams per cubic centimeter. That is project over here, 2.65. That is project over here, 2.87. Sorry, it's hard to control my pen on the computer here. And if you go over for the remaining one, which is limestone, that will be 2.71 over here. So that's the way these cross plots were prepared, so that the terminal point over here gives you the corresponding density of that mineral. So if you ever happen to need to memorize the density of these minerals? Well, you don't have to memorize them because you can come to these cross plots, project them on the left, and that will be the density of these minerals. Of course, you can do the same thing with anhydrite, and you can do the same thing with salt at the top. Now, please note that for density values, we have a wide range of possibilities. So it turns out that this value, as you take any point, let's say that you are in the quartz guide over here, then as you move on the quartz guide, your point, the porosity is increasing. And please note that the values that we have on the tick marks are values of total porosity of that rock saturated with water. As the porosity of that rock increases, but the solid composition of the rock remains the same, that is to say quartz, then all of the points will be aligned in that direction. That's what happens, it moves. So clean lithology. And how are these points calculated? Where those points are calculated based on the basic equations that says that the density of the rock equals the porosity times the density of the fluid plus 1 minus porosity times the density of the matrix. That's how they were calculated. Very simple. You know that the matrix is 2.65, the fluid is 1, so you can calculate the density. Now, if you happen to be in dolomite, please note that that would be your terminal density, and remember, and then as you increase the porosity of the rock, assuming that it's fresh water, all those points should be moving up in that direction. If you happen to have calcite, well, that's the same thing as it is here. This is actually a very interesting graphical point, because if somebody comes and gives you the apparent density porosity of quartz in some place, let's say 10, you have 10 here, you can always come and convert that apparent density to density, if you want, apparent porosity, to density. Or you can convert that to apparent density porosity in dolomite units or in calcite units if they want. That's one easy way to convert. The other thing that I want to mention is this. Look at what happens with the PEF value for a sandstone rock, pure sandstone with different porosities. As the porosity increases, of course, the point is moving up, but the variation in PEF for electric factor is not very large, because at the bottom we're at 1.8, and when the porosity increases to the maximum, which is 40, we are about 1.4. So 0.4 to 0.8, not a very significant range. Whereas in the case of density, the values have a larger, wide variability. For the case of dolomite, which is the central guide, the variation is a little bit wider, because we start from 3.2 all the way up to 2.6, approximately 2.7, approximately at the top. It's a little bit wider, but not as significant in percent as it is for the density. Similarly for the calcite starts at about 5 PEF, and then as it moves up, it decreases to 3.8, and that's probably the largest variation that we have for all three elements, all three minerals, as the porosity increases. So that's for limestone we see the largest variation of PEF. So we can say that compared to density, PEF is not as sensitive to the matrix composition. That's one of the important elements of this plot, that if you have PEF is by and large sensitive to the solid composition, especially at very low values of porosity. Very low values of porosity, then definitely this variation is minimal, even in the case of calcite. But as the porosity increases, then we have more sensitivity to the fluid. Now, please note that for the values of PEF close to 5, then we have some overlap with the values for the case of anhydrite and calcite. So if somebody would come and say, well, I have a PEF of 5, is not affected by barite, is not affected by any other thing, caliper, so it's a realistic, it's a precise measurement. What lithology do I have? Well, If you have 5, it could be 2. It could be anhydrite or it could be calcite. And if you have somewhere about 4.8, maybe even could be salt. So how am I going to differentiate between those? Well, because we need to use the density and PEF. With PEF alone, I would not be able to make the differentiation. But if I have the PEF and density, immediately I know that the points will fall either here or here. That's a very important remark about what happens with anhydrite and salt, that PEF alone is not. So, but if you have values of PEF close to 2, 1.8, most likely this will be close to sandstone and those rocks. Of course, in this case, it's a siliciclastic rock. Sandstone composed of mostly quartz. If, for instance, you have a rock that by happenstance happens to have some proportion of dolomite and quartz, then, or better said, let me just say this something which is more common, a proportion of dolomite and calcite. Let's say that your point is here. So why is it there? Well, if you think as a mathematician, it's here because it's not in the guides, because somehow the density of the material and the PEF of the material does not correspond to any of this. But let's say that somebody comes along and says, I know that that rock is a combination of dolomite and calcite, and I know that that rock doesn't have any quartz, so this is external information that you would know. Then obviously we know that is a combination of dolomite and calcite. And the question is, okay, how much of the two do I have? And what is a porosity if that were the case? Well, here's how it works. What we do is, if that's the case, if this is water saturated, and we know for a fact that it's only dolomite and calcite, the proportions that you have, discarding quartz and anything else, then we know, for instance, we can trace the guides 2020. I trace guides 2020, 1010. 1010 is hard on the computer to do this. I do the 3030 somewhere here. And then those are going to constitute the mixing between those two components. And essentially what this point is falling is about 21 if I were to project that. And the relative distance between, now that I know that it's 21 porosity units, the relative distance that I have from this point to the dolomite or the calcite is going to be an indication of the relative concentration of the solid parts that I have between the two. If I know that this point is getting closer to calcite, well, most of what I have is calcite. And if I know that the point is closer to dolomite, then that point will be dolomite. But the relative distance is normalized to the total distance will give me the concentration of those two. That's how it's done. Now, if the point were to be moved over here, of course, I will do the same process, finding the corresponding guide. That will give me the porosity, and the relative distances measured to each one of those guides will give me the relative proportions of the two. That's how we solve it graphically, if you will. But you see, it's because we're combining the density and PEF, and we're making the assumption that we know the end members. Now, what happens if that point now is this point here becomes a combination of, not very common, but let's say calcite and quartz? Then what I have to do is, okay, you tell me that you have only two end members. As soon as I know the end members, now I can do the guides between those two. And then I can do a similar procedure to see where this falls, what guide porosity corresponds, assuming that is water, and the relative distance that I have from the guides from the point to the end guides at that point will be me an indication of the relative concentrations. That's how it is. I could also do the same thing for the sake of argument between, let's say, quartz and dolomite or the like, so I can group. Potentially, I can actually use these plots in 3D, so to speak, where if I have the three of them, I could do guides that go like this, and then I could surmise that to be a triangle, and I see a triangle that is overlapping with the point, so that will give me the porosity, and then the relative distances to the vertices in a normalized way will give me the relative concentrations of the triangle. That's one way of doing it. It's a little bit more complicated. You can surmise that what I'm doing here is a system of two equations when I have two components, two equations, simultaneous equations, and if I have three components, it's a system of three simultaneous equations. Of course, this system is solvable because I'm assuming that everything is quartz. I'm sorry, everything is water. It gets a little bit more complicated when the fluid that you have is something different from water. But so far I'm giving you the mechanics of this analysis. I mentioned that you should not take into account clay or shale because when you have clay or shale, this can throw the location of the points as well. Now, what happens if I have a combination of anhydrite and let's say calcite, which is very common? I would have to do the same thing here. I would have to do the 5. Or if I have anhydrite and dolomite, will be something that I would also move in this direction. You can actually see that sometimes we might have points over here below the zeros. And you say, why is it below the zeros? It shouldn't be here. Well, it can happen if you have a combination of calcite, dolomite, and anhydrite. So anhydrite will tend to pull the point down to here. So there are cases, especially when you are in between this domain of dolomite, calcite, and anhydrite, that the point will be a combination of the three, and it will look like a very low, very high density. So that's something that we have to take into account. So that this is the mechanics of that, how this method works. Now let's go to the similar case for the neutron density log. The neutron density plot that we have here is done here for the compensated neutron logging tool and the lethal density tool by Schlumberger. The chart is pore 11. This chart makes the assumption that the fluid is fresh water. There's another chart that is for slightly saltier water. I have to remind you that in the case of neutron logs, because they're sensitive to chlorine, the choice of plot is very important. I tend to choose this one where 1.0 in the cases of, for instance, mud filtration by fresh water-based mud. Then because the measurements neutron and density are relatively shallow, sensing then it will be mostly sensing that type of fluid as opposed to the original formation water, which might or could be salty. But if not, then we go to the other chart, the 1.1, which is the pore 12, I think. Okay, so what do we have here? Similar to the previous plot, we have three guides. This is the quartz guide, and we have the calcite guide, and we have the dolomite guide. X-axis is neutron porosity. Please note that the x-axis is always expressed in limestone porosity units. It's not a problem if your neutron log is in sandstone porosity units, because you can always go back and forth and compare as we have been describing this in class. That if somebody gives you the neutron log in sandstone porosity units, let's say that somebody told you 35 sandstone porosity units, so I'm here, and if you want to compare that to limestone porosity units, you just position the point down vertically until it hits the calcite, and that will be the equivalent limestone porosity units for the neutron log. That's the way we convert. But in any case, when we use this, let's make sure that we know that the x-axis is limestone porosity units, but we can always convert. Okay, now the other thing is that density log is similar to what we had in the PEF, 3.0 at the bottom and 1.9 at the top. So this is a reverse scale in grams per cubic centimeter. Please note that. Okay, now there are other components in addition to quartz, calcite, and dolomite, as we had in the PEF cross plot, which is anhydrite here, and then we have the sulfur and salt over here. In the previous plot, dolomite guide was closer to the quartz guide, and calcite was the farthest away. Now for the neutron density, the situation is reversed between calcite and dolomite. Please pay attention to that. Sometimes on the y-axis on the second y-axis, there's equivalent density porosity in limestone porosity units. So there's a way to convert. But we can move back and forth horizontally across to convert the density, bulk density, into apparent density porosity for water, saturation for quartz. You can also get for calcite, and you can get for dolomite. So the conversion on the x-axis as it crosses the guides is going to give you the corresponding conversion for the density log, but for corresponding conversion of the matrix. But if you use the y-axis, then you can do the corresponding conversion for the neutron log in between dolomite, limestone, and quartz. Now, the guides are also prepared assuming that we have freshwater saturation in the porosity. If you walk all the way to the end of the guides over here, you are going to project this on the y-axis, and that's going to give you the corresponding density of the pure components. For quartz, you get 2.65. For the limestone, we get 2.71, and for dolomite, we get 2.87. That's the same thing that we got in the PEF plots, so nothing different. And now, if you project them to the x-axis, then you will get the corresponding neutron porosities. Please note that the neutron porosity for the sandstone matrix and limestone porosity units is negative. Why is that? Well, because of the conversion. Nothing to worry about. And hydrite also has very low values, negative values of neutron porosity, so pay attention to that. So what happens when you have quartz, and quartz is saturated with water, and the porosity increases? Well, then your points are going to be constantly moving along the guide. If you have a sandstone, a clean sandstone, mostly quartz in the matrix, those points are going, and the porosity is high, those points are going to the top. If you have a very tight siliciclastic rock, then the points are going to go to the bottom. So you see they are moving, shifting up and down as we have differences in porosity. Same for calcite. If you have a pure calcite matrix, then you are going to move over here. And last, if you have dolomite, then we are going to see those points moving back and forth. And this is the interesting thing, because as opposed to PEF, PEF is relatively insensitive to the fluids, but neutron logs are not. If you go into a fluid that is lighter than water, then what's going to happen is that your points are going to deflect to the left. Let me explain. Suppose that you have quartz over here, and you have fresh water, and you have, let's say, 25% porosity of rock. But now let's say that you substitute the water with some gas. Granted that there are many kinds of gases, but what's going to happen here is that the neutron log and the density logs are going to change because of the fluid being lighter than water. And you see this guy that says approximate gas correction? What's going to happen to your points is that they are going to move away from the sandstone line, almost in the parallel direction of that arrow. In other words, coming through here. It's hard for me to plot this, but imagine that this line is parallel to the arrow. So the lighter the fluid and the higher the porosity and the larger the saturation of the light fluid, the point will shift farther and farther away from here. So that's the problem when we have light fluids, that now you have a point here, and then you say, well, why is that point there? Well, we know that that point is there because the fluid that you have is lighter than water. But now you might say, well, how do I know that the matrix is quartz and not limestone with gas? Yeah, that could be the case. You can actually come from here and be a limestone matrix that has gas and move all the way here, or it could be a dolomite with gas and move over here. So yes, you can have all the cases. So that's the reason why when you have a light fluid, it's very important to corroborate, to verify, to combine these measurements with something that is less sensitive to the presence of a light fluid, in this case using the PEF and density. Now, if you happen to have a situation where you have barite, or you have a very old log that came from a tool that did not have PEF, because PEF became commercial. I don't know when, but not, I want to say maybe 1980s. But so if you have some logs that are older than that, then they will not have PEF. Or if you have a well that has an incredibly large or significant concentration of barite, then PEF is useless. So there's no way to do it. So you're stuck with the neutron and density cross plot. So it's important to do verifications. And like we did in the case of neutron and density, the density in PEF, you can have combinations of all of them. Let's say that you have a rock that is a combination of dolomite and calcite, just for the sake of argument, and that the rock is 100% water saturated. And then the point is going to fall here. So what's going to happen? Well, similar to what we had in the PEF and density, you can generate your guides by joining points that have equal porosity. And you extend it, and then immediately you know that porosity of this point will be somewhere between 15 and 20 based on the guide, and the relative distance that you have to the guide locations here will give you the relative concentrations of the two minerals in the rock, because that rock has partial limestone and partial calcite in its solid composition. Okay, so that's because you have two components. If you knew that the two components were dolomite and quartz, for the sake of argument, then you will draw the line here and here, and also that line will give you a different porosity. And because of the distances, you could calculate the corresponding concentration. So similar to what we saw with the PEF and density cross plots, these if you happen to have water saturation, and if you happen to know what end members you have at most two, then you can immediately, number one, calculate the porosity of that rock, which takes into account the relative concentrations of the solids. Remember that if you had the density of the two rocks, we have the density, porosity, density of the matrix, plus 1 minus porosity, density of the fluid. Of course, if we have water, this is 1. But let's say that the density of the matrix is a combination of the density of dolomite and the density of limestone. But in this case, let's say that you have 50%, 0.5, the density of dolomite, and 0.5, the density of limestone. Then we know that the density of the matrix will be a linear combination of the two. And that's how this point is moving. And then from this density of the matrix, now you can calculate the new porosity. And that's what this chart does the way I did it here. And so number one, if you know that the fluid is water, then you can certainly calculate the corresponding porosity of the rock if you know what are the end members of the two end members. And if you know the distance, and because you know that the two end members, you can calculate the relative distances to the guides, and those relative distances are going to give you an indication of the relative concentration. So two things you get, the porosity and the relative concentration. And you can choose your end members. If you have three, you will work with this triangle that I told you. Eventually, this becomes a quasi-linear system of equations, and then solving it for multiple components is hard to do graphically. You will have to do it on the computer, and there are many commercial softwares that can do this for you. But today, I'm going to concentrate on the mechanics of this chart. I show you how it works, both of them. And I'm going to show you examples of how you can differentiate between the different components, what do they say, and what do they entail. Okay, now, but please bear in mind what I said. Don't do these plots if you suspect to have caliper problems. Sudden caliper variations will cause problems with the density neutron logs. So we don't do that, and then you will get a weird point that makes no sense with the lithology. If you have barite in the drilling mud, make sure that you correct it for that. But if the PEF is higher than what it's supposed to do, don't use it. There are cases, for instance, where the gamma ray log could be very low, and then the PEF could be very high. And then you say, why do I have a sandstone porosity and the PEF is very high? Well, it turns out that sometimes when you have a porous impermeable rock and the mud cake is the thickness of the mud cake is significant and then is loaded with barite, that could affect the PEF, and then the PEF could land you in a place which does not correspond to the lithology that you have. So it's very important to take into account those effects. And that effect of shell, I'm going to show you examples, but it's also a significant one because you will see that in many cases, shell tends to drop points in places where you have dolomite. And if you're not alert to this thing and just plot and say, oh, that's a dolomite. Well, no, look at the gamma ray log before you say that. So that's the reason why we have to look at everything. We have to look at gamma rays. We have to look at resistivity logs. The other thing that happens is if you see that your points are moving toward the bottom of these plots, that means that your porosity is decreasing. And of course, we expect that if the porosity decreases, the resistivity should increase. So there's a way to cross-reference all these points. And the other thing that I want to say is that you have to take into account the volume of investigation of these tools, because if you happen to be in a thin bed, well, the points are going to go in different directions. Okay, let's look at examples now. Here's the first one. It's a synthetic example that is used to assess the effects of different compositions and also different fluids. I have this case for, these are the PEF density neutron logs for if the rocks were all water saturated. Here's the resistivity log. Now, if the rocks were all oil saturated, we will have these 3 PEF and density logs. And if the rocks were all gas saturated, we will have this. And for the case of oil and gas, because it doesn't matter for the resistivity logs, we will have the same resistivity logs. Okay, so now let's see how these plots look like. Let's begin with the PEF and density for the case of water. Okay, here we have water saturation. And that log was generated, that synthetic log was generated to have the corresponding bands in hydrite, dolomite, dolostones, which is a mixture of dolomite and limestone in some proportion, then dolosand, mixture of sandstone and dolomite, sandstone, shaly sandstone. Look at the gamma ray log, that's shaly over here, and then finally a shell. So if you plot those lithologies and their logs in the PEF neutron log that I saw, these are the sandstone guide, this is the dolomite guide, and this is the limestone guide, then what's going to happen, and this is the anhydrite, what's going to happen is this, look, all the points that are in hydrite are going to fall here. All the points of limestone are going to fall here. Dolomite, limestone in between, over here in between the dolomite. If you have dolomite, they're going to be here. And if you have dolostone between sandstone and dolomite, somewhere here. If you have sandstone, over here. And what happens when you have a shell? Look, depending on the shell concentration, they are going to fall somewhat close to dolomite. This is not necessarily the case, but certainly they're going to get away from the sandstone guide. In fact, look at this. We have a shaly sandstone. Now it's not on the sandstone guide, but it's moving far away from it, on to the left. That's typically what happens. How far away? Well, it depends on the type of clay minerals that you have in the shell, and it also depends on the shell porosity, volumetric concentration of shell, number of things that you have here. But look, when the points, also another thing that I want to mention is as the points move down on the guides, the porosity decreases. So look at this. The limestone rock that we have here is the one that happens to have the lowest porosity, and similar to the anhydrite. Dolomite happens to be in between, and then the sandstone has probably the highest porosity. If we go back and look at the resistivity logs, which are here, you're going to see that in effect, when the porosity decreases, the resistivity increases dramatically. I shouldn't say dramatically because that sounds like drama. Substantially, let's say. But that's in hydrite, high values of resistivity. And then when you have increasing values of porosity, then the resistivity decays. And look at that, it's decreasing for the case of sandstone. So there's a reality check here. That's what we see. Now, what happens with the same PEF versus density if I do oil saturation now? Look at this. Compare. Boom. Let me go back and forth. Here, now oil. What's going on? Well, essentially the points are moving up. Why are they moving up? Because as we place oil in the matrix, the fluid gets lighter, the density decreases. So that's the reason why the points go there. But PEF is relatively insensitive to that. So all the points are moving. We have to take that into account. So they're departing from the guides a little bit to the right just because of the deflection of the guides. And that happens more for limestone and dolomite. For sandstone, it's the same, it's just moving up. Now, what happens if I replace the water with gas? Look at this. Take into account, take a shot, boom, everything moved up. So that's the effect of the fluid. The points are moving up. And so it's very important to remember that if you are going to use these charts to identify or to calculate porosities, well, that calculation of porosity no longer holds because it's made on the assumption of fresh water. But nonetheless, the proximity to the guides remains because PEF is relatively insensitive to the presence of light fluids. Relatively insensitive. So the relative locations are going to indicate what you have. Okay. Please, again, let me just make sure that you understand that when you have shaly sandstones, don't confuse those with dolomite. Please don't do that. What you have to do is you have to look at the gamma ray log. In fact, the color of these points that you have here, if I didn't mention, that color is based on the gamma ray log. That's the scale of colors here. So whenever you have high values of gamma ray, which in this case would correspond to shales, then your points will get red. If your points are, if you have a clean sandstone, then your points will become maybe blue here. And that's how we can recognize also by labeling the points according to the value of gamma ray log. Alright, so please don't forget, it's very easy when you focus on these plots, just to think that you have those logs and then don't take it for a face value, especially if you have shale. Okay, now let's look at the neutron density cross plot for this example. Okay, here we go. Same example, water saturation, and everything looks nice. Here's the guide for dolomite, here is the guide for limestone, and here is the guide for sandstone. Our sandstone points are here, a little bit more compressed. Shale points are here, the shale points are here along the dolomite, along the limestone, sorry. Look at this now. They're closing themselves to the limestone, not to the dolomite. And hydrite is here, as we indicated, limestone is here. As the points move toward the left, that means that the porosity is decreasing, so the resistivity is increasing. So obviously the sandstone points are the ones that have the highest porosity. That's what we see here. And please note that these clusters are also color-coded with the gamma ray log, so that's important to know. And the shading that you see here on these logs is actually shading that goes with the color of the cluster that was chosen to each one of these particular examples. Okay, let's go for the next one here. What happens if I have oil saturation? Please see this. Boom. What's going on? Let me just go back. Water, oil. What's going on? If you look at these points, they move that way. And why are they moving that way? Because that's the direction of the light fluid. And why so? Well, because in this case, the neutron log is extremely sensitive to the presence of the original fluid. Of course, when you have invasion, some of this fluid is not obvious, clear, or the effect is not as substantial as we see it here, because part of the fluid would be mud filtrate. Or if you have oil-based mud invading, well, you will see a similar effect. But that's what I want you to see, how the points are moving. Now, what happens if I replace the water with gas? Look at this. So this is water, this is oil. Are you ready for gas? Here is gas. Boom. Did you see that? Let me just go back. This difference. Now move to gas. Why is it moving? Essentially, the points have a tendency to move like this. And that's what happens. So we have to be very careful not to take the neutron density guides for face value, because we know that this effect is implicit. I want to remind you that in the case of PEF density, that effect was not nearly as substantially. Now all the points are away from the sandstone guide for instance, we had some dolomites or some limestones that now have climbed over the sandstone guide. So not because they are here, now you can say that they belong to the sandstone. No, it's the effect of the fluid. So we have to be very careful with this situation where we analyze lithology. So in summary, if you compare the PEF density versus the neutron density, we will say that the PEF density is a little bit easier to understand the composition, but for neutron is not as simple. Okay, now let's go to another example. Let's look at a carbonate example. Let me just remind you what carbonates look like this. This is the Edwards Formation, not far from, actually over Austin. It's part of the Edwards Aquifer. We have limestone, we have other components, and in this case we have some porosity here, some porosity here. So just bear in mind how different logs are going to look like. In general, what we see is that the gamma ray log here, if you don't have any potassium, uranium, and thorium, it will be very flat. The porosity of these rocks will be very low, except in cases where we have some degree of bugginess. But also that will have good porosity and low resistivities. When you have very low porosity, the resistivity will be extremely high. So let's look at that in those, keeping this sequence in mind. So here are several examples that I want to tell you. And I mentioned that I was going to start with carbonates, but let me start with the example that is the case of the deep water Gulf of Mexico, which is page 1 and 3 of the 358 well log compendium. We'll return to carbonates in 1 second. So what I have here is the original log that we have on the compendium that has gas, oil, and hydrocarbon. That's the original logs. But then what we did on the computer is to take those logs and modify them so that all the fluids are water. All of the fluids are water. This example doesn't have PEF logs. So let's see what happens with the neutron density plot of this example when it's 100% water and when we have the gas. Okay, are you ready? Let's go there. Here, when you have shale, and this is for only water, okay? This is for only water case. This is what happens. First of all, this is the sandstone guide over here. And the pure shale points are all right here. And how do I know that? Because of the values of gamma ray log. You see, the color of the points is indicated by the corresponding value of gamma ray log. Okay, so see, shales appear to be close to the dolomite guide. So when you do something like this, please don't confuse shale with dolomite. What we do is we eliminate shale from the cross plot. So if you do that, the elimination, you get this. Eliminate the points. And now it's easier to understand which ones are clean and which ones are not. So it turns out that shaly sandstones are going to be in this area and the clean sandstones are going to be here. Now look at the cluster of points. This cluster of points has moved drastically from the guide in this direction. In fact, if you look at the values here, you're going to see they're between 30 and 35. And we know that those rocks have about that porosity, somewhere in between 30 and 35, as we calculated before. If that sandstone were very tight, then those points would have come all the way here, and the resistivity logs will be much higher. So this is one example of how we can anticipate from those plots what kind of porosity and what kind of fluid we have. So this is for water. Now, what happens if I go back to the field case and I let the gas and oil be what they are? Okay, here is what happens. Just for reference, this is when you have only water, and this is the gas effect. Or the points, these are the points that are in water in the field case, and these are the points that are in gas or oil in the field case, oil and gas. And that's exactly what we saw in the synthetic case, that they will tend to go over here. And that's typically the gas effect that we see on the neutron density cross plot, similar to what I mentioned before. Okay, now let's go to another example. Here, back to carbonates. So let's focus now on carbonates. I should have shown the clastics after the fact, but let's show on carbonates. First of all, this is one of the examples that we have in the consortium, in the compendium, pages 8 to 12. It's an example from the Williston Basin in the US. This is where the back-end wells are. And this is a carbonate sequence. I want to mention, first of all, that we have some caliper problems here, so we don't want to look at anything. Now, this carbonate sequence is very interesting. Look at the gamma ray log here. The values are extremely low, almost flat as a pancake. That's what we expect in a carbonate sequence that looks like this. Very low values of gamma ray, relatively no uranium potassium concentration, very clean. So we expect the gamma ray log to look like that. Very clean, except in some other places here. But we have to be aware of these caliper problems because they can throw the logs. For instance, look at the density log that is completely abnormally showing abnormally high values of density. Same here. So we have to eliminate those points. This is a sonic log. Here we have the resistivity logs. Please note the scale of the resistivity logs, 200 ohm meters or even more right here. Here we have the PEF. Here we have the neutron and density logs. These logs are all expressed, the neutron and density logs are expressed in limestone porosity units. So we can go directly to the cross plots. And please note something interesting, that the lowest values of resistivity are over here. And those are the reason why the resistivity is relatively low. And please note the logarithmic scale is because these points have the highest porosity. And please look at the difference between shallow, medium, and deep resistivity. We see signs of invasion. So this formation has good porosity, or these formations have good porosity, and they have permeability because they manifest signs of invasion. So that's good. Now let's look at the cross plot. So here is the neutron, the density PEF, and this is color coded with the gamma ray. So all points have very low values of gamma ray, so that's good. But let's see where the points are. If you remember, at the bottom of the sequence here is anhydrite. And lo and behold, those points are the ones that have the super high values of resistivity over here and over here. Very low porosity, super high values of resistivity. Those are the anhydrite points. Now, what are the other points? Well, it turns out that the bluish kind of points, the greenish kinds of points here, those are the ones that are enclosed by the green, the semi-green scale here, or cluster here. And those points are a combination of dolomite and limestone, but with very low porosities. How do I know that you have low porosities? Well, because the points are coming to the end of the guide. You see that? So where do we have now presence of limestone? These are the points, and you have to those are the pink points. And we have a few points that seem to be limestone, but very spotty places. Most of it is dolomite or a combination of dolomite and calcite. We also have combinations of anhydrite and dolomite here. So we have this combination, but those points have very low porosities and the resistivities are extremely high. The good porosities of this example are all over here. And how do I know that those are good porosities? Well, because the values are going up, you see, and they tend to be closer to dolomite than they are to limestone. So I would say it's not necessarily full dolomite because they're not aligning here. Remember that we have some invasion, so and the mud is water-based mud, so we have that, but the proximity to the dolomite line or guide compared to the limestone, it tells me that the dominant composition here is dolomite. So if I were to assume that the dominant mineral is dolomite, then I could easily calculate the porosity by taking the values over here. And what are those points? Turns out that those points are these points. Those are the good points. You see, those are the points that have the highest porosity, therefore the lowest value of resistivity, and those points manifest invasion, so we have a good permeable rock. So all the rocks that we have in this example, obviously those are the best ones for candidates of presence of good storage and flow properties, and why not presence of hydrocarbons. Let's look at the neutron and density plot now. Same example, and what we see, these are the different guides. What we see here is, this is the dolomite, and again we see very good coincidence of the points, and in fact depending on where the points are, these are all blue circles, so all the bands that are blue correspond to this circle over here, and those are relatively high porosity, and in fact the best points are at the top over here. Very good, if I read the numbers, are close to 25-30% porosity, and those are the ones that come in this area. They align very close to dolomite, or closer to dolomite, with maybe some points jumping over here, slightly indicating presence of light fluid, as we saw before. And then we have a collection of points that are dolomite, limestone here, and then most of the points are very low porosity because they're at the bottom of the sequence, at the bottom of the guides, and we also understand that we have anhydrite here. And the points that you see here in green, these points, they look abnormal, and these points are because of potential caliper problems. So we have to neglect those points. So what I want to note here is that we have an interpretation that is consistent for PEF and density. PEF is working fine, no barite problems. In fact, if you go back to the example here, you could read potentially the depth of these, the mud weight, and so forth, and based on those, density of the mud, 10 pounds per gallon. So with those, you can assume that there was not enough barite to destroy the PEF logs here, so they work well. So that's another example of how this works in a carbonate sequence. Now, let's go to a more complex carbonate example. This example is also part of the, no, this is not part of the compendium, so it's a separate example. That's the reason why I don't illustrate. But here we have the caliper, some caliper problems, potentially, some places. We have the gamma ray log, we have the spontaneous potential log. The fact that we have the spontaneous potential log is already telling us that this drilling mud is water-based mud. Then we have the resistivity logs. Please pay attention to the values. 200 value over here, so this will be 10 over here. Please note the signs of invasion in some places, over here, and over here. Please look at the values of porosity based on the density log, both the density and the density log here is in Sanson porosity units, but it can be easily converted to any other lithology that we want for calculation. In software, actually, these conversions are relatively simple to apply. But what I want to point out is that it seems that this point over here has very low porosity, and that's the reason why we have high resistivity. So we have to understand. And also, when we look at these, if we want to assess the dominant mineral composition, it's also very important that we always focus on places where we have the minimum possible values of gamma ray, because high values of gamma ray like this will most likely be associated with shells. So we want to minimize the impact of shells if we want to see an analysis. So if somebody comes and says, okay, what is the dominant mineral composition here? Well, good news, I have the neutron density logs and I have the PEF log. I know what matrix was used in the density in the neutron log. I also look at the resistivity logs, already indicating to me presence of invasion or not, and also values. And I know where the good porosities are. Perhaps the best porosities are at the top and also at the bottom here. And also I recognize where I have good, I have shells that I need to not take into account, not to confuse, and I also have indications where the caliper log might be affecting the reliability of the density measurements. Okay, so let's go and plot. First plot, PEF and density. What do we see here? Okay, so here what I have done is I did this plot, but I totally eliminated the effect of the shell layers, the effect of the shell layers. And what we see here is that there's a tendency for the points to align between dolomite and limestone. This is for PEF. In most cases, we also have a few points with abnormal composition here, limestone, and those are the points that are listed here with the blue over here. But most of the points tend to be between dolomite and limestone. So what is the composition here? Okay, so, and the other thing that is very important to see is that if especially we compare this cluster of points with the previous example, is a tendency to move in the upward direction. So that is also already indicating to us that they have good porosity. We don't see any presence of anhydrite, and then we have some abnormal points here that we need to find out what they are, because most likely they will be associated with bad caliper or something else. Okay, so far it seems like we have a combination of dolomite and limestone. And when you have the PEF log, and you can rest assured that the PEF is not affected by drilling mud, number one, because if it were affected by drilling mud and we are oblivious to it, then this could be a sandstone that has moved everything to the right. But we have to verify that this is not the case. So I'm assuming that the effect of barite in the mud here is not significant. Also, I have to verify that for those values of gamma ray, that those values are sufficiently low that we don't see problems with the presence or not presence of shell here. Okay, so now let's look at the neutron density log. So here is a plot, and again the neutron and density log is going to be indicative of light fluids. So here's what we see now, that there are some points that continue to be in the limestone, but there are some points that continue now is in the limestone and dolomite, and there are some points that now have moved all the way up to the sandstone. And what are they? And these could be interesting. Those points are in the bluish, and potentially this could be a light fluid present in the limestone dolomite lithology that has shown the effect to move that way because of the presence of a light fluid. And that's important that we recognize, because this plot is definitely not consistent with the PEF plot. If you remember, in the PEF density plot that we had here, there was no indication of a sandstone lithology. Now, when we go to the neutron density, we have an indication of a sandstone lithology. And then we might ask, so what's going on here? Because the green points are here, and now the green points are moving to the top. So what's going on? This cannot be a clean sandstone either, because if it were a clean sandstone, then it would have shown here with the PEF over here. So most likely what's going on is, in this example, is we have some presence of hydrocarbons in the dolomite limestone lithology that have moved the points way out here. And that's something that we can recognize from this example. Okay, let's go to another example here. Mixed carbonate sequence, mixed sedimentary sequence in clastics and carbonates. This is on page 18 of the well log compendium, part 2. Please note that we have calipers. In fact, we have some caliper problems, calipers on imbrications here. So we have to be mindful of those. And in fact, you can see that when we have caliper problems, the density log complaints and exhibits relatively high values of porosity, which are non-realistic. And those are the points that we have to never use because they are abnormally affected by the caliper. So the density, which is a pad tool, was not making proper contact with the formation, and that caused a problem. So we have to eliminate those points. The other thing that I want to do is I want to eliminate points that have high values of gamma ray log that could be associated with shells. So with all of that said, let's do the cross plots but eliminate the effects of shells and eliminate the effects of the presence of caliper problems. I also want to point out in passing this log, which is the gray color here, that's showing the delta density log. And please note that the delta density log, which is the density corrected, it correlates extremely well with the caliper, you see. So now we know that those bad caliper problems, they were corrected real time by the logging tool, and the size of the corrections is large in places where we had bad caliper. So that gives us confirmation of points that we should not take into account when we do this cross-plot analysis. Another interesting thing, if you look at the resistivity logs, is to understand where the logs have good porosity, and that's where you have lowest resistivity, and lowest resistivity here, and some points that have potentially high resistivity here, but that's also affecting high resistivity, but that's low porosity. So we have indication also of the presence of invasion in some of these units based on the differences between the deep sensing and the shallow sensing logs. Okay, so let's look at this analysis, make sure that the cross plots are also consistent with the other logs that we see in this sequence. Okay, and before we go there, I just have to mention this is a mixed sequence, so we have some clastics and some carbonates, and here's a beautiful example from Spain, where you have an interaction between the alluvial fan deposition intermixed with marginal marine facies, carbonate dominated facies, and all the transitions that you have there. So this is one example of how these rocks could be generated by Mother Earth. And here's a cross plot. The first thing that we see is we have, this is PEF and density, some points that definitely have a high component of limestone. Those are the points that come in blue here. Okay, all the bad points with caliper have been eliminated, so have been the shells eliminated, and we see a combination of the sandstone and dolomite or sandstone limestone composition. So here's an interesting point, right? When you have combinations of sandstone and carbonates, it could be sandstone and then within the volume of investigation of the tool, and it could be partly limestone and partly dolomite. I want to point out that the points for limestone, because they're way at the bottom of this guide, they exhibit very low values of porosity. The good points seem to be the ones that are a combination of clastics and carbonates. And the reason why this doesn't seem to have 100% quartz constitution is that if it were quartz constitution, it would have been already on the spine over here. So that's where we see, and in fact, if you look at the green cluster, those are the green points over here. All of them mostly significant presence of quartzites, but also presence of calcareous material. And that's the reason why the points do not align. So let's look at this now in the context of the neutron density. Okay, here's a plot. Now what we see is that we don't reach the sandstone guide over here. The points continue to be between the sandstone and limestone. That's very good. And most of the points tend to be high porosities here. We have also some limestone points that we saw before here. that align toward the very low values of porosity, and those we cannot take them into account because they have very low porosity. So the best rocks in terms of storage are here, and those are the ones that come as conclude the principle or the identification that we saw before in the neutron in the density path plot. So we see that effect. So here's how we have a common description between the two logs, and the reason why it's common here is most likely, and we see this from the resistivity logs, that the sequence does not have hydrocarbon. It's a water saturated sequence, and because of that we don't see the effect of presence of hydrocarbon as we saw it in the example before. Okay, now let me summarize what we just said. Okay, so to do the analysis that I just went by, it's of course important to look at all the logs, including the resistivity logs. It's important to eliminate any points that have sudden caliper variations, because we know that the density log is going to give us values with abnormally high porosities in those cases, and of course the neutron log is also affected by that. In order to be able to eliminate any effect by shell, we have to do this analysis at local minima of gamma ray, and the values of gamma ray, they have to be relatively low. We also cannot apply this in very thin beds because of the averaging effect. We may have to make sure that all of the environmental effects have been corrected for in the neutron logs, and verify that matching effects. Please look at the records and make sure barite is not a significant or does not have a significant effect on mud cake. And remember that mud cake happens to take place in porous and permeable rocks, and those are the ones that more likely we want to quantify, identify, and assess their storage and flow properties. Pay attention to all the mud filtrate invasion effects, because that's going to tell us that the rock is permeable, and resistivity logs are very important to verify the corresponding porosity effects that we see manifested in the cross plots. It's important to also verify that the cross plots are not affected by fluids lighter than water. We saw that PEF and density cross plots are much less sensitive to the presence of fluids lighter than water, especially the PEF. And this is somewhat mitigated in the presence of invasion with water-based mud, because if that's the case, the original hydrocarbon is not going to be as visible by the neutron or the density logs as it should have been in the case of no invasion. The other important thing is salt may cause some problems with the neutron logs, so we have to make sure that these logs are not affected by that. So to identify the dominant lithology, we have to use the PEF density and the neutron density logs in combination with the resistivity logs. Make sure that we have a common story here, and we have to verify these with mud logs and any core data that we have at our disposal. But when you do all of that, this is what happens. So let's say that you have your neutron and density logs now, and you want to, first of all, you want to assess what is the dominant matrix composition, so that you can in turn calculate the porosity. And so what we do is, with the cross plots, we have those three plots, and the density logs or the neutron logs are given to us either in sandstone, limestone, or dolomite. The most common thing is that those two logs are given to us in sandstone or limestone. So now, to calculate the porosity of the rock, we go through the cross plots, and then we identify the dominant matrix or the combinations of the two. But let's say that lith is the dominant lithology. So what we have to do is, once we know the dominant lithology, then we express both the density and neutron logs in that dominant lithology. For instance, if we found out that the logs were given to us, the neutron and density logs were given to us in limestone porosity units, but the dominant lithology for a given point, a given depth in the log is sandstone, then we have to convert them to Sanson. Likewise, if the density neutron logs were given to us in Sanson Porosity units, and that might have worked well in one section of the well, but in another section of the well, we find that the dominant lithology is limestone or dolomite. So what do? Well, we need to convert the density neutron logs from sandstone to the dominant lithology, either limestone or dolomite. Okay, so that's what this is. The C stands for lithology corrected. So now we correct it. And now we see the following. What happens if, after the correction, the neutron log is larger than the density log? That's a bad condition. Of course, we have verified that gamma ray log or presence of shell or clay is not a problem, because that's the way we selected these points. So then we have a problem. Lithology is incorrect. So we need to go back and refine the assessment of lithology. Look at everything else, because if the lithology that you use to express the neutron and density logs is correct, then you should have a condition that is either the corrected log neutron should be very close to the density log, and this happens if you have water or you have invasion with water-based mud, and this would be deep invasion with water-based mud. Then this is inspection. And then, of course, if somebody says, so what is the porosity of the rock then? If the two logs are very close, then most likely the porosity of this rock is either the neutron or density logs. They are close, so it should be the same. Now, what happens if the neutron corrected log is less than the density corrected log? Then we know, when you have made that correction, that the dominant fluid is lighter than water. So that's good. We get happy, right there, happy face. And then how do we calculate the porosity of the rock then? Okay, so here is the calculation. Remember this calculation that we applied for shell laminated sequences when we corrected for presence of shell? The same thing. We essentially the logs that were given to us in a given lithology, but that lithology may or may not be the correct one. So we assess what the lithology is depth by depth. So we do this analysis depth by depth, because in complex rocks the lithology is going to be variable with depth. So we have to analyze this effect, the neutron density cross plots, the PEF density cross plots. All of these needs to be analyzed to assess the dominant composition. And once we assess the dominant composition, then we express both neutron and density logs in that, and then we confront them, we analyze, and we go through this sequence of steps. If everything is wrong, we have to go back and redo the analysis. And then if it's equal or not, we can now understand the presence of the fluid lighter of water. And of course, this situation can be verified with resistivity logs. So we have additional information to know. And then once we correct, then we are safe to calculate the porosity of the rock. Very simple. And now, what happens if you have a more complex situation? So I show you how to do this when you have one or two minerals. Okay, so we know what the mineral is. But what happens when I have more than two or three? Well, it turns out that you can apply a quasi-linear system of equations where you have multiple mineral elements, and you know what the properties are for those elements. And then what you do is you give me the log at any point right here. You give me the density, the neutron log, the sonic, any other log that you have at your disposal. And then, of course, with those, I know that I can form a quasi-linear system where the system of unknowns is the concentrations of the given elements and the porosity of the rock. And then I know that all the concentrations, they need to be positive, and I also know that all of the concentrations, they have to add up to 1, and they have to be smaller than 1. So what I do is now I can force a linear system of equations. That's what we are doing with this graphical analysis, essentially. But of course, the more individual minerals that you have, the more rows that you need to solve the system, more data. So you cannot have 20 minerals and only 3 data points and try to find the concentrations of all of those and the porosity of the rock. That would be a very ill-determined problem that you cannot solve. But when you can do a minimization in least squares or something subject to constraints, And that's how some of the commercial software works. It's not really that difficult to implement. The only issue is that sometimes when you have presence of gas or partial saturation, you have to take that into account when you calculate the logs. But that's the general approach. Okay, so what else can one do with the PEF and spectral gamma ray logs? Well, there's another way to identify clay minerals. Let me just show you one example. We saw this example in the presentation for spectral gamma ray logs, page 45 of PGE358 well log compendium. And that was interesting because we analyzed spectral gamma ray logs and we went and did the analysis based on spectral gamma ray logs. So now we looked at these gamma ray logs and we cross-plotted them. We used this cross-plot from Schlumberger, the LITH1, where the x-axis is potassium, the y-axis is thorium, and then we cross-plotted them and we found where the points would lie, mostly kaolinite or mixed layer in this example. That was one of the things we found based on slides in the relative thorium to potassium ratio that we have here. And we also found, based on the gamma ray log, that both sandstones and shales have the same dominant clay minerals. Okay, now let's do another plot that is often used for this. If PEF is working fine, is not affected by mud cake, presence of barite, and so forth, so on, then we can do cross plots between PEF and potassium, or PEF and ratio of thorium to potassium. And the consequence is that the plots, the discovery analysis plots, are a little bit more granular than in the case of spectral gamma ray logs cross-plotted themselves. And this gives us a much more granular way to determine the dominant clay mineral composition. So let's do the plots. Here are the logs. We have the spectral gamma ray logs here, and then we also have the PEF, and we have, please note that we have the delta density corrected here in neutron log, so we can do all of the analysis. And here are the cross plots. For if you just let only sandstone go through the analysis and you use a plot of potassium in percent versus PEF, this cross plot, then you're going to find out that all of the points aligned in the same group. So it's a combination of elite, it's a combination of mormorillonite and kaolinite. All of these are, but mostly mormorillonite, which is a smectite, in kaolinite, and that's common for both sandstones and shales. And that's actually what we found from the potassium versus thorium cross plot before. Okay, now let's look at the other cross plot. Thorium ratio of thorium over potassium versus PEF. And the points are for two sandstones and for shales. So we separated the same cross plot, but one for sandstones and one for shales in that. And what do we find? We find that most of them are in the kaolinite smectite mixed layer point, and that's consistent for all of the sandstones and shales. So this analysis is also not only consistent with spectral gamma ray logs themselves, but also with the previous plot that we had for PEF. And so this is another way of doing the clay type analysis when the photoelectric factor log is working fine, is not affected by caliper, and is also not affected by presence of barite in the mud. All right, so that concludes the lecture. It's a very long lecture, but I hope you were able to follow them. I hope you enjoyed it. I hope it was informative. And let me summarize by saying that dominant mineral composition is necessary for accurate porosity calculations. Essentially what they give you is the density of the grains, which you can use to calculate porosity. But when the fluid variable is not water, then we have to also invoke and use neutron logs. We know that this situation, that the matrix cannot be made assume constant when you have carbonates or mixed sedimentary sequences. And the density path and the neutron density cross plots are extremely useful for that. They provide guides in analysis. I show you the basic elements of working with those plots. The fluid effects cannot be neglected. Sometimes they're very confusing. If we don't have the PEF log and just the neutron and density logs, often is not very easy to identify those. So in cases where PEF is not available, it's very important to, for instance, in a carbonate sequence, to do the neutron density cross plots in places where we have mostly water saturation, and we can use those points as reference. Of course, we always have the mud logs, the well logs, the core data. It's always very, very important to do reality checks and to verify all the information with the different logs, so that the interpretation that we make is in harmony with everything else. There are no contradictions, loopholes, or any other problem. And it's very important that we do quality control of the logs, and we identify these lithologies with the least possible influence by shale, clay, and also where we know that the logs are not affected by barite or by caliper. Very, very important. And it's also very important to verify that the well logs have been properly depth matched and that all the environmental corrections were applied to them. Good. So there are some review questions. There are many. This is an extensive topic, so I have a few here. I'm just going to go slowly so you can read them on your own. But this is essentially a review of the basic principles of operation of density, PEF, and neutron logs separately. And the questions are going to ask you basic queries about the origin of the principle whereby these measurements are made. What do they measure and how? What is that they're affected? How is that they're combined? What are the elements of the engineering of the tool? Compensated systems, interpretation corrections that are applied, the utility of interpretation procedures, the effect of matrix versus the effect of solid, etc., etc., etc. And I also want to acknowledge, again, Joshua Bautista Anguiano, our TA, helped me a lot to produce many of the plots that I use in this presentation. We are going to have exercises based on the analysis. Just please remember the elements that I just mentioned. I had the summary of steps that one has to do to recognize the porosity, to recognize the dominant mineral composition when you have combinations, also very important. I also wanted to thank Baker Hughes and Schlumberger because I'm using some of their material with their permission to produce this presentation. And with that said, happy logging, happy mineral composition analysis. Please apply these principles to the homework and let me know if you have any questions. I hope the presentation was not too long, but I do hope that it's very informative and clear. If not, please send me emails, ask me questions. I'm all open for suggestions, and I'm more than happy to implement all your comments to make this better. Okay, hook and horns. Thank you.